In this video, we're going to set you up to be able to integrate for area moments of inertia. The formula is relatively straightforward. Ix is equal to the integral of y squared dA. Iy is the integral of x squared dA. And if you choose the correct dA, it isn't too bad. It's not too bad at all. But if you choose the wrong dA, it's actually very complicated. And it's different than our centroid integrations that we did. Our integration for centroids lets you use almost any dA as long as you chose y tilde and x tilde correctly. It's a little bit, it's different for area moments of inertia, and I try to help you to appreciate that. So I'm going to share the screen, and we're going to talk through this. So your first hint that something's different is actually in your crib sheet. So if you look at your crib sheet, for centroids, x bar, then the numerator is an x tilde dA. For y bar, it's y tilde dA. Where x tilde is like a distance from the y-axis to the centroid of the dA, the y tilde was a distance from the x-axis to the centroid of the dA. And you could pretty much choose any dA you wanted to, as long as you defined x tilde and y tilde correctly. But notice that Hibbler on his crib sheet, when he defines Ix, he doesn't use a y tilde. He uses y squared dA. And for his Iy, he doesn't use an x tilde. It just uses x squared dA. There's a reason for this. There's a reason he chose to do this. And if you choose the correct dA, then the proper y is just y, not a y tilde. And the proper x is just x and not a tilde. And these formulas, as written here, only apply for properly chosen dA. If you choose the wrong dA, this formula doesn't work. More on that. So again, for centroids, you can choose any of three dAs. You can choose a dA that's like dx dy or dy dx. You can choose a horizontal dA, or you can choose a vertical dA. And all three worked as long as you chose the correct x tilde to the centroid of the dA, or the y tilde to the centroid of the dA. They all three worked. So again, why does Hibbler use these definitions without x tilde and without y tilde? And the short answer is these guys, again, don't apply for every dA. And for the cases where they do apply for dA, then the y tilde is y, or the x tilde is x. And so he doesn't use the tildes on purpose to not confuse you, but about something that's inherently confusing. So what dAs can you use? So as long as you use the right ones, they're relatively easy. So in my opinion, the easiest dA to use for area moments of inertia by integration is a dx dy or a dy dx dA, and then just use a double integral. If you do it that way, then Ix is always y squared dA, Iy is always x squared dA, and everything's straightforward. Another approach that also works is that leads you to a single integral is if you're looking for Ix, choose an element that's parallel to the x-axis, where the entire element is a distance y from the x-axis. And so Ix, in this case, is the integral of y squared dA. The dA is like x right minus x left times the dy, and y squared is y. And so that works. Or if you want to find Iy of this area, then you'd use an element parallel to the y-axis, where the entire element is a distance x from the y-axis. And then Iy is the integral of x squared dA, and the dA is equal to y top minus y bottom times dx. And that works nicely, and our definitions work. But where you get into trouble is you basically use this element parallel to the x to find ix. And you basically say, I'm going to use this same element to find iy. And I'm just going to say iy is equal to the integral of x tilde, which is some distance from my yx to the center of this guy, squared, times the dA, however defined it. And if you do that, you will be wrong because it doesn't work. The same here. If you choose to take this vertical element and take him around the x-axis, and you define a y tilde from him down to the x-axis, and you square that guy, and you define the dA, and you say, that's my ix, you would be wrong. You can't do that, okay? Why is that? Why can't you do that? I'm glad you asked. That's the purpose of this video, is to explain to you why you can't. So fundamentally, what you're doing when you write this integral is you're actually taking, you have a dA, and you're moving, and you have that dA has its own moment of inertia about his centroidal axis. And then you're moving that guy down to the x-axis, or you're moving that guy to the y-axis. And so you actually have to use the parallel axis theorem to relate his I bar about his centroidal axis down to the x-axis or to the y. And so the most fundamental equation that does work for all dAs at every orientation are these. So Ix is the integral of dix, where dix is the moment of inertia of the dA about the x-axis. And Iy is the integral of the diys, where the diy is the moment of inertia of the dA about the y-axis. And these work for every dA, but they're complicated because you have to use the parallel axis theorem for your dA to get the dix or the diy. Hang on, it'll get clear here in a moment. So remember the parallel axis, and we actually will derive it in a video soon, but we mentioned it earlier. So for general area, it has a centroidal axes x prime and y prime, and a distance dy to the x-axis, and a distance dx to the y-axis. And so the I about one of these axes is equal to I bar about the centroid plus the area times the distance squared, either to the x-axis or to the y. So more specifically, if we want to take this, find the moment of inertia of this area about the x-axis, is Ix is equal to I bar about this x prime axis plus the area times the dy squared. If we want to find the moment of inertia of this area around the y-axis, then that's the I bar about the y centroidal axis plus the area times dx squared. Hang on, I know this is complicated. So for whatever dA I'm using, I'm technically have to use the parallel axis theorem in differential form. So hang on, I'll explain it. So remember, you have a horizontal element, you have a vertical element, and you have the little dx dy element. But all three of these are rectangles. And so remember, for rectangles, our I bar for a rectangle is 1/12 bh cubed in all three cases. So we have to write the parallel axis theorem in differential form. So remember, our Ix is the integral or the sum of the dix's of our dA. So the dix, which is the moment of inertia of my dA about the x-axis, is equal to di bar about the x prime axis of my dA plus the dA times the y squared. I shouldn't have said y tilde, I just should have said y. and diy about the y-axis of that whatever dA that you choose is di bar about the y prime axis plus dA times x squared. So what does this mean? How do we apply this? So let's first apply this principle to an element that's parallel to the x. And so if our element is parallel to the x, and we're wanting to find ix, di bar about an axis parallel to the x, it's 1/12 base times the height squared. But it's the height cubed. It's bh cubed. It's bh cubed. That should be a cube. So it's 1/12 base times dy. The h is dy, and that's cubed. And so that guy goes to 0. And so the di bar term goes to 0. And I'm left with a y squared dA term about the x-axis. And so if I choose a horizontal element and apply the parallel axis theorem to this dA, the I bar term drops out, and I'm left with y squared dA, which is my original defining formula. So life is good. This is easy. We can do this. But what if I choose an element that's perpendicular to the x-axis? What does that look like? So I'm still going to write Ix is equal to the sum or the integral of the dix's. But the dix's are the moments of inertia of this dA about the x-axis. So I actually have to use the parallel axis theorem to move the I bar to the x-axis. And so the I bar term is 1/12 bh cubed. It's 1/12 bh cubed. And so it's 1/12. The base is dx. This should be dx, the base. And the height of this guy, the h, is y top minus y bottom cubed. And the y tilde is the average of y top and y bottom. So it's y top plus y bottom over 2. So when I say that the Ix of this element that's perpendicular to it is equal to the integral of the dix's, well, that's equal to the integral of the di bar term plus the dA times the y tilde term squared. And so my dix, or my di bar, is 1/12 dx y top minus y bottom. It's cubed. It's cubed. Plus y tilde squared, which is the average of y top and y bottom squared, times the dA, which is y top minus y bottom times dx. And that's dA. So if you choose for when you're integrating for an area moment of inertia, and you choose an element that's parallel or that's perpendicular to the axis of interest, this is the way you have to do it. No other way works. But this is painful. So the real lesson is don't use an element perpendicular to the axis of interest. Use the dxdy and a double integral, or use an element parallel to the axis. And then it's relatively straightforward, and you should be able to do it. But just be careful with this. Obviously, if you're looking for a good time, you might want to work one of these all the way out. Not. But it's complicated. It's complicated. What about the element like the dxdy element? Let's apply that to that as well. So remember our dix is di bar plus y squared dA. And our dix bar, our di bar is 1/12 bh cubed. And it's a 1/12 dx times dy cubed. And so all of these differential lengths go to 0. So my di bar term is 0. And so I'm left with y squared dA about the x-axis. And I'm left with x squared dA about the y-axis. So it works nicely for the double integral. There's actually one other case where I can use a element that's perpendicular to the axis of interest. So remember, for a rectangle, I bar is 1/12 bh cubed. Well, a rectangle area moment of inertia about his base is 1/3 bh cubed. And so if I have an area that touches the x-axis, if I chose an element that's perpendicular to the x-axis, but that element touches the x-axis, I can write Ix is the integral of the dix terms of the dA. And again, that's a general formula that works for all of my dAs. But because this is a rectangle, and because he touches my x-axis, I can use the I base form for him. And so his I base is 1/3 bh cubed. And so 1/3, the base is dx, and the height is y cubed. And of course, because it's a dx, you have to convert the y to the x function that defines it. But that's relatively simple. Ix is 1/3 base, which is dx times y cubed. And so that's straightforward. The same is true for the Iy. So for the Iy, if you have an area and you want to find Iy, you can choose an element that's perpendicular to the y-axis because it touches it. But then you have to use the 1/3 bh cubed formula for the diy about its base. And so you have a 1/3, the base is dy, and the height is x cubed. And of course, you have to convert that to y, but that's your Iy. So again, in general, don't use an element that's perpendicular to the x or perpendicular to the y. However, if the area touches the axis, you can use the I base, which is 1/3 bh cubed. Occasionally that shows up on a test where it kind of asks you a conceptual question about that. And it's certainly a tool in your toolbox. But like everything else, know what you're doing. Know how to use your different tools. And so as long as you know what you're doing, then you can choose the easy ways and you're smart enough to avoid the impossible ways. So this will get you started. In the future, in upcoming videos, we're going to work some example problems of it by integration. But this gives you a conceptual framework for which DAs we're going to use and which DAs to avoid.